Hi, John Valvano here, and in this video we're going to review interrupts. Now you had interrupts in 319K, but we're going to focus in on the aspects of interrupts that are germane to 445L. Now we have a multi-threaded environment, which means we have the main program which is running as usual, and then we have one or more interrupt service routines which will comprise of the background threads. All right, and we're going to share information between these threads in global variables. All right, the first concept I want to discuss is that of priority. Now in this diagram we have two interrupts. We have an interrupt running at priority 4, which is a low priority. It goes from 0 to 7, where 7 is the lowest and 0 is the highest. And we have a second interrupt enabled at priority 2, which is higher than 4. And the main program comes, and then this interrupt 7, the priority 4 interrupt, gets triggered. Okay? And so in this orange blob here, we're running the interrupt 7, the priority 4 thread. But before that interrupt service is done, we trigger a interrupt 2, which has got a priority of 2, which is higher than 4. So it will push the 8 registers on the stack, suspend that interrupt service routine, launch this higher priority one, and it will run uninterrupted because it's the highest priority on our system. When that one finishes, it will do a BXLR, popping 8 registers off the stack, and then we resume and continue the lower priority interrupt until it is done, another BXLR, which will pop 8 registers off the stack, and the user program is resumed. So this essence of priority gives us the ability to establish which threads are important. And for those that are really important, we give it a high priority. And for those threads that are less important, we give it a lower priority. Okay. Now, the idea of the interrupts and all their nested beautifulness is implemented in here in the nested vector interrupt controller. And rather than going through all the details that we did previously in 319K, I encourage you to review the ebook section 6.3 from 319K to see how this NVIC works. Okay. Again, one of the important aspects that we have to deal with when we have multiple threads is priority. It turns out there's a register in the processor which lets it know at what priority is it running at. So in particular, if I'm running in an ISR with priority 3, any thread which is 0, 1, or 2 can suspend that, but any thread that is 3, 4, 5, 6, or 7 will be postponed, not dismissed, postponed until the higher priority is done. Okay. Now let's talk about some terminology. Okay. We have an idea called ARM, which is in the device. Because there are hundreds of bits that could interrupt, we'll arm just those bits which we want to cause interrupts. Okay, so we typically do this at the beginning. We arm the device we want the interrupts. We arm the flags we want to interrupt, and we disarm all the others. Then there's a flag bit. Okay. This flag bit is the essence of interrupt. An interrupt is a hardware-triggered software action. That's what an interrupt is. And the hardware trigger is going to set this flag. Okay, and that's what that begins, that initiates, that triggers the device. Okay, and we can look at it. It's typically in a register called RIS. All right. There's also the I bit. The I bit is in the processor. It's in the PRIMASC. It's in the PRIMASC register inside the processor, and I equals 0 means enable, I equals 1 means disabled. In our code, we're going to call these two functions to enable and disable. And again, disabling interrupt doesn't dismiss the interrupts, it postpones them. All right, so we talked about the ARM bit in the device. There's also an enable bit in the nested vectored interrupt controller. And so what I'm saying here is 4 things have to happen for an interrupt to be triggered. We enable it in the nested vectored interrupt controller. We arm it in the device. In the processor, we set I equals 0, and then the hardware generates that trigger. Now, these 4 steps can be in any order. Typically, these are done during initialization, typically. And this is done over and over again while it runs, okay, while we're running. But could be in the other order if you wanted. All right. Again, let's focus in on some of the differences between 445L and 319K. Because we want a real-time system, we are going to define the term latency between the time that the trigger flag is set. Okay? The trigger time is set. All sorts of interesting stuff has to happen, and then the interrupt occurs. It runs the ISR, and then for an input device, we're going to read the input. Now, for an output device, we would write output, and we're going to define this time delay between the setting of the flag and performing the function needed by that flag as latency. Okay? In a hard real-time system, this latency here is always less than some bound. And this bound is a very small bound. That's why it's called hard real-time. Okay? Now, with a periodic event, we'll talk about latency in a different way. We'll talk about this issue of jitter, and there's another slide coming up, and we'll talk about jitter in a moment. All right. Now, in a periodic event like sampling the A to D converter or outputting to the D to A converter, so we can go D to A output, we can do A to C input, or we can actually run a control algorithm which does input, calculate, output. Okay, a control system would do an input, calculate, output sequence. And the idea of a periodic real-time system is though the time in which I do this event, output to the D to A, input from the A to D converter, or run the control system must be at exactly a periodic event. Okay, so we want the delta t of that between one output to the DAC to the next output to DAC. We want that to be some sort of some sort of bound. In other words, if we take the sampling rate and we invert the sampling rate, we get time, and we can talk about a delta before and after. Okay, the delta before and after, the time between the interrupts. So again, I'm doing this. I'm getting an interrupt, and they should be exactly 1 over fs. But if the interrupt is delayed, okay, then this delta t will be large. This delta t1 will be large, and this delta t2 will be small. And that's what's illustrated here in these two pictures, and that is the time, right? That's this delta t here, the time between interrupts. In this case, if I'm trying to run at, my sampling rate here is 1 kilohertz, I'm expecting exactly 80,000 bus cycles between the triggering of the sampling on the ADD converter. Now, if my main program runs with no divide instruction, you will see that I will take 1,000 samples, and the time between the interrupts will be exactly 80,000 for all 1,000 times. On the other hand, if my main program has a divide instruction, the divide instruction takes 12 bus cycles, okay? And occasionally the time between the two interrupts is not perfectly 80,000. Now, typically this jitter is small. If the jitter is plus or minus 2 bus cycles, nobody cares. But if I have an environment with 2 interrupts, the jitter on the low priority interrupt is going to be huge. All right? Look at these numbers. Now that's like 50 bus cycles, because the existence or running of the high priority interrupt causes the low priority interrupt to be imperfect. Okay? Again, the idea here is we put our most important tasks at high priority, and they'll have a low jitter. And we put our less important tasks at a lower priority, and they will have a small but not negligible jitter. It's important for us to understand this if we're going to define our system as real time. All right, so how do we evaluate our system? We just talked about latency. Latency is the time between a request and a service. Another parameter that's often ascribed to our system is how much data can it process, how much real data can come in and be processed and go out. If we're talking about a communication channel, then we can talk about throughput, which is like the average bandwidth that it can establish. Just like everything else in this class, you can't use a term by itself. You always have to say, I define latency as the time between when an I/O device is given a command and when that command is completed. Or bandwidth is the maximum data flow or capacity of a channel. You got to define the term before you use it, because these are not consistent throughout the literature. All right. When we're trying to go fast, it's always good to put our finger on the bottleneck. And so if you think about what it takes to process data, data is going to be a combination of input-output or hardware, CPU bus cycles, or software. Okay? So there's always both of which have to happen in order for data to be processed. But when we design a system, we measure a system, we debug a system, we try to optimize it, it's good to put our handle on what the ratio is, which one of these two factors is limiting the ability to process data. In an I/O bound device, the speed, the number of bytes that can come in, get processed, go out, is limited by the hardware. That's what I/O bound means, which means if we make the I/O device faster, the system will run faster. Unfortunately, if the bandwidth is limited by hardware and I make the software run faster, it doesn't actually get better, okay? Because the software is just waiting for the I/O to happen. On the other hand, if the software time is large compared to the hardware time, right? Again, the speed is a function of both of these, but it's possible that the speed of the system is limited by the software. So therefore, increasing the algorithm, the bus cycles, the processor speed, getting a better processor, whatever I can do to increase the software speed will have an impact on my performance. I can run 2 processors, 3 processors, 4 processors in parallel. That's an example of how I would make my software run faster. All right, lots of timers. Most of what we're going to do this semester is actually going to be a periodic timer, and so again, you've seen timer in 319K. Go ahead and review it. Look at the code. If your job is to understand every line of your code, except for Lab 4. That's the internet's way too complicated for you to understand it all. But all the other labs, I want you to understand every line of code. So as you're using your code, if there's some line you don't understand, either look it up or come to office hours and ask questions. Okay. Again, there's 8 timers, 0 through 7. They're 32 bits. They generate periodic interrupts. The rate, the period of the interrupt is basically going to be tail R plus 1 times the clock, and the clock actually has a prescale if you want it. There's a prescale. And then the eventual 12.5 nanoseconds of our 80 megahertz clock. Okay. Again, you're allowed to use the code on the book, on the ebook, on the starter code, but I need you to understand all the steps. Okay. All right, let's talk about something else, and that is signal to noise ratio. Okay. So if you think about a signal that we've measured in our computer, we're gonna unfortunately have errors or noise added to it. And so when we look at this simple model of the data that we've collected is a combination of the actual true signal that I was trying to measure plus added noise. Now the noise could come from the A to D converter, the noise could come from electromagnetic fields, the noise could come from white noise, pink noise, purple noise. It could come, there's no purple noise. Okay. Now, what we're going to do is the obvious thing in the noisy environment is rather than take just one sample, X, okay, just take one sample, X, and take that, what we're going to do is we're going to take N samples and average it, okay? Now, the power in doing that is the central limit theorem. So if we assume that this noise, the noise of one sample is independent from the noise of another sample, that's independent noise. And if we assume that whatever noise probability creation, whatever distribution that noise has, is the same for all the noises. Okay, and the shorthand is independent, identically distributed. That's a shorthand for these two statements. And once you make those assumptions, we can deploy the central limit theorem, and it turns out that the average, or the sum, either way, the average of samples will lose whatever probability density function it had and become Gaussian. And the cool part is if the average noise, if the noise average is 0, what'll happen is as n gets large, it'll approach the true signal mu. Okay, so if mu is the true signal, x sub I is a single, the sum of the x's is capital X, then expected value of the average will approach the true value, and the standard deviation goes to 0. Here's an experimental example of this. If we take a single sample here, right, n equals 0, n equals 1, that's the big dots, and this is a constant input to the A to D converter, and I do it 1,000 times. I take 1,000 samples, I produce a probability mass function. Of that data, you'll see that the distribution here, this distribution here, it's got 2 humps. All right, and a very large standard deviation. Okay? Whereas if I take n equal 4, right there, right, I lose the 2 humps. And the standard deviation goes down. If I take n equals 16, my distribution is very Gaussian, and it has that n equals 16. It has a very small standard deviation. So the signal to noise ratio, which is mu over sigma, gets better and better as n increases. Okay? You'll discover this in lab. So again, the central limit theorem gives me the authority to average data together in an effort to improve signal to noise ratio. All right, we saw one experiment. Here's another one. Again, the difference between the two probability distributions. This is n equals 1. There's actually a register in the TM4C which will do the hardware averaging for you. But if you see, there's a bunch of dots. You see them all down there? This has got a very large standard deviation and not Gaussian. Whereas at n equals 64, basically all of my points are exactly the same. Now the cost of averaging is power and time. Okay. Now with the TM4C, I can set the SAC, the sampling average control, to 6, and I'm not losing processor time because it happens in hardware. Okay, so in summary, interrupts are a big deal in this class. I want you to understand latency as it works in your program. We need to discuss how well it works, and so we'll be using the word bandwidth, but I need you to continue to define it before you use it. Priority allows one thread to have more importance than the other, and then you really got to understand the trigger flag. That's the hardware event which causes the software action. The software will then clear. The software typically will clear the interrupt by doing an acknowledge, and then the first couple of passes through this class, through interrupts in this class, we're going to use timer, and therefore when you use a timer, periodic timer to produce a regular rate software execution, you need to be able to calculate, understand, and minimize jitter. All right, have fun.